Good, good day, everyone. In this project, I modify project 1 on the Cucumber board to read data from multiple sensors using independent pre-RTOS tags and display all the latest reading on a web server with accurate timestamp. This implementation uses Wi-Fi connectivity and a simple web dashboard that refreshes every 10 seconds. So the first step in the code is importing the required libraries. As you can see here, we have 9 libraries. The wire.h, which handles the I2C communication between the ESP and sensor. The Wi-Fi.h connects the ESP32 to your Wi-Fi network. Then the ESP-MDNS.h, which allow us to access the board by name. Then the web server.h, which provides a lightweight HTTP server. And we have the following 4 libraries. These libraries handle sensor communication and data conversion. And last one is the time.h, which is used to synchronize and format timestamp for sensor reading. These libraries make it possible for the ESP32 to collect, organize, and serve sensor data over the Wi-Fi. Next is the Wi-Fi and MDNS setup. So in the Wi-Fi section, I define the network credential as you can see here. We have the Wi-Fi SSD and the Wi-Fi password. Then the ESP32 connect to the network using the Wi-Fi.begin/SSD SSID and password. Once connected, it prints the IP address of in the serial monitor. Then I initialize the MDNS with the host name Cucumber, which lets me access the board at http://cucumber.local instead of remembering an IP address. But I used to connect with the ESP or Wi-Fi network provided in the serial monitor, as you can see here. Immediately when the sensor starts, the Wi-Fi connected and the IP address will be printed here, which I will use later on when I am going to show you the reading from the sensor in the web page address. So next is the time configuration. The code set up network time protocol to get real world time from the internet. So here the GMT offset is set to 7 hours, which is Thailand time zone, and the daylight offset is 0. This ensures every sensor reading has a real time stamp in the format year, month, date, as you can see here. Next is the LED. I define the built-in LED as an output. It is mainly for debugging and indicating the board active status, though not central for this project, but is used to debug. Then next I initialize the sensors. So in this project, I use 4 sensors connected through the IC2 bus. The first one is BMP280 for pressure and temperature reading. Then the HTS221 or HST4X for humidity and temperature. And the last one is the MPU6050 for acceleration and gyroscope data. So initialization is done using the .begin function for each sensor. If a sensor responds correctly, a corresponding plug like HSABMP or like this one is set to true. Next is sensor data structure. Yes, this one, sensor data structure. To keep everything organized, I define a structure that will upload the readings from the board. A global variable last reading holds the most recent sensor data from all tags. Every time a tag updates its value, it also updates the timestamp field with the latest time. And next is the time formatting function. This function converts the raw time value from NTF into a readable string format like 2025 1103. This formatted time is then shown both on the serial monitor and on the web page. Then next is the FreeRTOS sensor tags. This project uses 3 free RTOS tags, each running independently over 10 seconds. The first one is BMP 280 tags that read the pressure and temperature and update last reading dot pressure and last reading of temperature, then print the BPM 280 update, as you can see here in the serial monitor. So this is what is really happening in the BMP 280 tags. And the next one is the HTS 220 OS HT4X tags, which is here. It's responsible for humidity and temperature. Then the last one is the BPU 6050, which is responsible for acceleration and gyroscope data on all the 3 axes, X, Y, and Z axis. Next is after these 3 taxes, I moved to the HTTP handler. I use the web server class to create a simple HTTP server on port 80. There are main 2 routes, the slash, which serve the HTML dashboard, and the slash data, which provide the same data in JSON format. So this allows both browser and potential data fetching display via API. So this is the section I'm talking about. The first one is building the page, and the second one is the handle of data. Next, I move to the setup function. In this function, I started the serial monitor for debugging, then configure the LED fin and initialize all sensor over I2C. Then I connected the Wi-Fi. And start the MDNS. Then I configured the NTP time system and started the web server and reached the endpoint. Then finally create the free RTOS tags for each detected sensor using the X tags create, BPM tags, and this one, which is the final scene I did. This is what I'm talking about. Yes, it is the last step for creating the pre-RTOS tags for each detected sensor. So almost close to the end, which is the loop function, which is very short. There is nothing inside except the server.handle client. Its only job is to continuously handle incoming HTTP requests while all sensor tags run in the background. This separation between networking and sensing keep the program responsive and stable. So now I will move on to the lab demonstration on the web page so that you can see the reading of the sensor data from the board. Okay, now I have my fresh page, so I will go and take the IP address here. If I copy it and in the new tab I paste it and press enter, you can see the real-time measurement printed here, whereby we have the temperature, humidity, pressure, acceleration, and gyroscope timestamp. So now I will blow some air from my mouth to the sensor and see whether the temperature will increase or decrease. Yeah, as you can see, the temperature slightly changes. Yeah. So to summarize, I separated each sensor into an independent free RTOS tags running every 10 seconds, and all readings are combined into a single structured data variable. The latest reading and timestamp are displayed on a web dashboard that auto-refreshes. The system supports multiple sensor types, the HTS 221 or HST4X automatically. And finally, this approach improves readability, scalability, and reliability. For example, future version could easily log data to cloud storage or trigger alerts when thresholds are exceeded. So this is the end of this presentation. Thank you.